Hello everybody, my name is Geeta Saumit. I'm from VVAT College, CSCC. So today I'm going to say about DLD seminar, and the topic is designing the synchronous counters. So before going into the topic, we need to know what is meant by a counter. So counter is nothing but it is a type of sequential circuit which counts the clock pulse. These circuits mainly designed to count the number of clock pulses occurring in a time duration. So the number of different counts possible in a counter is known as a modulo. To design a modulo n counter, the number of flip-flops required are log n to the base 2. So the number of flip-flops, as counters are also sequential circuits. To store any data or to access any data, we need only flip-flops which perform better activity than latches. So here we use mostly we can use any type of flip-flops like JK flip-flop, SR flip-flop and T flip-flop based upon the type of flip-flop synchronization, whether they are synchronous or asynchronous counters. So based upon the counting direction, the counters are classified into either up counter or down counter. Up counter is nothing but which counts from the sequential order, that is nothing but 0, 1, 2, 3, 4 and so on. It counts in a sequential order, whereas down counter comes from the highest value to the lowest value, that is 9, 8, 7, 6 and so on. So based upon the flip-flop synchronization, counters are also classified into two types. They are mostly synchronous counter and asynchronous counter. Synchronous counters are they are having same clock pulses, whereas asynchronous counters have different clock pulses. So as our topic is about synchronous counters, designing a basic synchronous counter, we will see what is meant by synchronous counter. Synchronous counter, the clock pulse or a clock signal is given to every flip-flop will be same. The flip-flop, all the flip-flops works on the same clock signals in the synchronous counters. So the clock pulse is given same to every flip-flop, and the operation will be performed with those same clock signals, and whenever the clock signal occurs, the operation will be performed. So the main advantage of synchronous counters is the operation will be faster and there will be less error generated than compared to asynchronous counters. Asynchronous counters, as there will be in asynchronous counters, clock pulses are not equal, they are not same. So each and every flip-flop has different clock pulses, so it takes time. The propagation will be uh, less compared to the synchronous counter, and it also takes a time. The operation is not that much faster when compared to synchronous counters, whereas these counters are mainly useful for frequency generator to count the count of frequency that is generating. So let us design a basic synchronous counter and let us see how to design those synchronous counters. So for designing any type of synchronous counters, it is necessary to know the excitation table of that particular flip-flop. So a synchronous counter can be, as the counters can be designed with different flip-flop levels. Let us take a T flip-flop example. So let us design a synchronous counter using T flip-flop. So we need to know, it is necessary about to know about the excitation table of T flip-flop, because it helps in further accessing of the table. So the excitation table of T flip-flop is given by, so this is the table of T flip-flop, excitation table of T flip-flop. That is, Qt is the present state, this is the next state, and T is the flip-flop input, where Qt and Qt plus 1 are taken as inputs in the excitation table, and T is taken as output. So when present state and next state are same, the output will be 0. That means that value of T will be 0. The present state is 0 and the next state is 0, so the output is 0. If any one changes, even it may be present state or next state, the output will be considered as 1. So here for 0 1 the output is 1, and for 102 the output is 1. For 1 1 the output is 0, as the both inputs are same, present state and next state. So this is the basic information about excitation of table of flip-flop. Now let us design a decade synchronous counter by using a T flip-flop. Decade in the sense is nothing but it counts only 10 values, that is mainly from starting from 0 to 9. So it counts from 0 to 9 only, but whenever the 10th value comes, it should be treated as 0. So it should count only 0. It should count only 9 values, and the 10th value is not occurred, and it should again return to 0 and perform the activity. So to design a decade synchronous counters, let us considering this is as up counter because you are going in a sequential order 0, 1, 2, 3, and so on. This is a decade synchronous up counter. So to design a table, we need the present state. Present state we are taking as A, B, C, D, and we are considered next state as A bar, B bar, C bar, and D bar. Now, how to represent these present state and next state is at initial the present state is 0. The next state should become 1 because it should count from 0 to 9. When the present state is 1, it will be 2. When it is 2, and it will be 3. When it is 3, and it will be 4. And likewise, when it is 8, it will be 9. And when it is 9, it should not be 10 because it counts only 9 values. 0 to 9, almost 10 values are completed. And whenever it comes 9, the next state should be considered as 0. So in that way, the decade synchronous up counter acts. So after representing all the present state and next states, we need to determine the flip-flop inputs. As we are using a T flip-flop, we also discussed the excitation table of T flip-flop. So now we are going to determine the flip-flop inputs TA. So consider only A column and here A column. When the present state is 0 and the next state is 0 in A, present state is 0 and next state is 0, there is no change in the state, so the output will be 0. And same when it is 0 and it is 0 and it output will be 0. And here when you see at the 7th, here the 7th number, the present state is 0 and next state is 1. At the 8th column, the present state is 0 and next state is 1. The output will be 1 because there is a change in any one state. It may be a present state or next state. So like this, in this way we are going to determine for each and every column, that is for TA, TB, TC, and TD, we determine flip-flop inputs, 4 flip-flop inputs. And now we had completed a table, writing table, and now we need to determine this table in a form of functions. So the output should be in a form of functions. It should be in a form of present state. So the one and only best method we have to represent a function, to simplify a function, is nothing but a k-map. As there are 4 variables are present, we need a 4 variable k-map. So for determining the outputs, flip-flop inputs TA, TB, and TC, TD, we need a 4 variable k-map. So drawing all the 4 variable k-maps for all the 4 inputs TA, TB, TC, and TD, we will get as like this. Here we are also considering down care condition. The down care condition we are considering because the synchronous counter, decade synchronous counter counts only up to 0 to 9. But the ninth value consists of 4 variables. It should be of 4 variables, that is 1, 0, 0, 1. For considering 9, for 4 variables are very necessary, and 9 can be represented in 4 variables in binary form. So the remaining values 10, 11, 12, 13, 14, and 15 are not used here. So the unused combinations are taken as don't care in this K-map diagram. So in the K-map you can see that 10, 11, 12, 13, 14, 15 are taken as don't cares. So here for TA, the output will be 1 in the column of at 7 and at 9. Consider only present state. At 7 and 9, the output will be 1. So here at 7 it is 1 and at 9 it is 1. The output is 1. So the don't care also helps to simplify the K-map. So after simplification of this, we will get TA as AD and AD plus BCD. Similarly, writing the same K-map for TB, TC, and TD, they are different. For TB, the output is at 3 and 7. 3 and 7, the output is 1 for B. So considering all these, we will get TB as CD and TC as A bar D and TD as 1, logic 1. So here we are going, we completed writing the K-map. So each and every flip-flop input is represented in the form of a function, that is in form of a present state. So the now last and final one we are going to determine is to draw the circuit diagram. So the circuit diagram, final circuit diagram looks like this. So at starting, we considered a flip flop. We need 4 flip flops to represent this, as we were discussing about decade counter. I represent these 4 flip flop which names A, B, C, and D. So for the flip flop TA, the function is AD plus BCD. The A is nothing but only the Q value which is of 8th flip flop. The Q value of 8th flip flop is represented as A, and the D is coming from the D flip flop, and the AND gate is present here. For BCD2 there is an AND gate, and these are connected to the OR gate, and it is given input as T. Similarly for D we are giving logic 1. For TD we are giving logic 1. Here you can see that for D there is a logic 1. Whereas C we are giving A bar D. For TC A bar D is given, so A bar is taken from Q bar at 8th flip flop. So this Q bar is connected to the D. This Q bar is connected to the D, that is nothing but A bar D. It is given input as C. For B, the function is CD. So we need to connect C and D to the B flip flop. The C is coming from here. Here there is C, and we are taking it here. D is taken here, and the AND gate of both C and D gives us CD, and it is connected to a input B. So here we can find that the clock signal is same for each and every flip flop. The clock signal is common for each and every flip flop. Common clock signal is found here, and this is nothing but design of synchronous decade counter. Synchronous decade counter, which counts only 0 to 9 values. So this is about the synchronous counters. Thank you, one and all.